Hi, and welcome to Science Unboxed with Professor Matt View, where we learn about science and much more and make it accessible to everyone. Eventually, this podcast is to really help us understand quantum theory, how it relates to subatomic particle theory, and how particle accelerators work, and hopefully help break down some of the barriers we have in understanding the science. Today's topic is the beginning of quantum physics. Why is it important and how is it different from regular Newtonian physics? I'm going to go over that and much more and break it down so you can understand. So why is quantum physics important? Why do I go on about it? How is it different than Newtonian physics? Why can't we just use Isaac Newton's old equations in the modern day? Well, obviously we have relativity, and we know about Einstein, and we know all about Stephen Hawking and a lot of popular scientists of the 20th century and how their equations are not based on Newtonian physics. They're really based on quantum mechanic theory. Basically, the whole idea of quantum mechanics and quantum physics comes down to that word quantum. Quantum means quanta, or it comes from the word quantity of matter or quantity of energy, specifically of energy. And what happened in the early 20th century is Newtonian physics was in a dilemma. It had four serious problems. First, there was the existence of these things called atoms. Now, we take that for granted today, and very few people know this, but one of Einstein's four seminal papers in 1905 helps to prove the existence of atoms. It's actually a chemistry paper of all things, not relativity. So atoms just existing. That shouldn't happen in Newtonian physics. Second, there was a problem with the spectra of light. Different elements emitted different colors. We had no idea why that happened in the early 20th century. Third, there was this incredible problem called the ultraviolet catastrophe. And the ultraviolet catastrophe basically said that anything that emitted radiation, anything that emitted heat, so me and you, we emit heat. Anything that emits heat should actually emit an infinite amount of energy. Now, obviously that doesn't occur, and everything has a quantity that it emits. So we know that's not true as well. And then the fourth problem was this thing called the photoelectric effect. And the photoelectric effect is really cool because you can actually set up at home. And Einstein actually proved the photoelectric effect and performed the photoelectric effect and proved it for quantum mechanics. And you can do the experiment at home. So what the experiment really is just you can take a test tube, okay, and you can take some type of metal, and on the bottom of the piece of metal, if you put a cork on top of the test tube and you put basically a piece of metal going down through almost like a needle, and you put a little aluminum foil on, two pieces, and then on the top, you have just a disc, another disc of metal. What happens is you can actually charge the metal so that the aluminum foil actually separates, showing that there's extra electrons in the metal. And most people don't know this, but metals have this interesting property where the reason why they are a metal is that they basically have a sea of electrons on top of them. And these electrons can move in and about pretty much where they want. They're not really attached to the atom in a metal. And that's what makes a metal different from a non-metal or a noble gas, because you have this free movement of electrons. So what I can do is I can use static electricity, actually just use a balloon and charge this device that I made out of a test tube. And I'll show you a picture of that. And I can charge it with electrons. Now, there's different types of this experiment where you can actually hook it up to a battery and you can actually create a current, but we don't need to do that. We just need to show that you can add the extra electrons. So now you have more electrons on this metal. You've charged it, okay? It has a positive charge. That means it has more electrons, okay? And basically what happens is if you shine light on it, suddenly the electrons will fly off. They'll just fly off into the air. How you know this is the aluminum foil that spread apart and actually comes together. That's very interesting, isn't it? You basically were able to eject electrons. And Newtonian physics did have an answer for this. It said basically the electrons were getting enough energy, and so they were able to cut the string of the atom they were connected to, and they could just fly off. But it didn't account for a very specific problem. They found that different colors of light, and actually whether or not it was ultraviolet, that means more than purple light, a color higher than purple, ejected more electrons or ejected them faster with more energy than did, say, the spectrum closer to red. And then going so far down below red, it actually didn't eject any electrons. That means the aluminum foil didn't come back together. It would stay apart. It didn't have enough energy to release those extra electrons. So that's a real problem for Newtonian physics, because Newtonian physics said that, well, if I increase the intensity or luminosity of the light that is hitting the disk and ejecting the electrons, then I can eject the electrons. There shouldn't be a problem. It shouldn't be dependent on color. Color has nothing to do with it. Well, color did have something to do with it. And so you had all these problems. Again, existing was a huge problem. The spectra of light and it being different colors was a huge problem. The ultraviolet catastrophe was a major problem. And the fourth problem was this photoelectric effect. And we actually see the photoelectric effect today in car door openers and different types of electronics that detect light and sensors in terms of opening doors and such by detecting light. Now, it was very simple. It was a very simple device that I'm talking about, but it's become more advanced. And we now use semiconductors and different aspects to create the photoelectric experiment or the photoelectric cell to detect light. So we had all these problems. And Einstein comes around and he actually applies a recent theory of another physicist named Max Planck. And Max Planck actually, he's famous for the Planck constant in E equals hf, or energy equals the constant h, which is the Planck constant times the frequency of the light that you have, or the electron frequency. And frequency is the amount of repetitions per second that it goes. So Planck used this constant to explain away the ultraviolet catastrophe. He said, basically, there is a graininess to the universe, how much energy something can be to produce radiation. And that becomes the Planck constant. It's close to zero, it's near zero, but it isn't quite zero. It's something like 1 times 10 to the negative 33, or 33 zeros before 1, times 10 to the negative 34th. It's a very small number. It's very close to zero. But the point is, it's not zero. And it's just like the speed of light. This becomes a problem with relativity, different from quantum mechanics, but related. Light was so fast that it was virtually infinite, but it wasn't infinite, right? It was we can actually measure the speed of light. It's a finite amount. And just like that, Planck constant says there's a finite amount of energy everything has to have. Can't be zero. So the Planck constant is applied to many things. It's applied to the photoelectric effect. Einstein applies to the photoelectric effect to say that light is quantized, that meaning that light comes in these packets. And up until that point, the accepted theory was actually against Newton and was Young and Huygens' view that light was a wave. And there was many different types of experiments to actually prove this. And even Einstein used light as a wave to prove relativity. But Einstein said, wait a second, light takes on this particleness. It comes in discrete packets of how much energy it can have. And that is basically the beginning of quantum mechanics. It's just saying that there is a quantity that things come in, that especially waves, things that we generally think of as waves come in, especially light. Now, it's eventually later proven that everything is somewhat a wave. And the real way to think of the world is in terms of waves and fields and field lines, and there are no real particles. A particle is really just the highest amplitude of a certain wave, but that's a little bit later. But that's the basis of the photoelectric effect, that you needed a discrete amount of energy to actually have the electrons absorb so that they could free themselves from the metal and actually allow those aluminum foil points coming back into the photoelectric experiment going back down. So discrete amounts, that amount of energy is related to the color and frequency. The color can tell us how much energy the wave has, and red has less than ultraviolet, X-ray, gamma radiation. If it was red light or less, the electron wouldn't get enough energy and it wouldn't be able to jump off the metal. Whereas if it was closer to the blue wavelength, it could jump off the metal. That's what is the beginning of quantum theory. This is also applied to atoms, and who applies this to atoms is Niels Bohr. It's a little bit different. It's about the angular momentum that the electrons spin around the nucleus of an atom. And he says that there's a smallest amount of energy, a angular momentum can have. Okay, so it has these orbitals, and there is a lowest orbital. It can't be right next to the nucleus. It has to be a little bit farther from the nucleus. Nucleus meaning where the protons and neutrons are. And eventually you find out that neutrons and protons are made out of quarks. So that is the four problems we had with Newtonian physics in the early 20th century, the late 19th century, early 20th century. And they're broken down quite quickly. So the common thread to all this is Planck's constant. Einstein might have come up with the idea explaining the photoelectric effect. Niels Bohr may have explained atomic theory, atomic orbital theory, but Max Planck's constant is really the factor that connects all of quantum mechanics. And interestingly enough, it was a fudge factor. It was a factor that he kind of didn't have an explanation for. He came to this problem of the ultraviolet catastrophe, and he said, well, if I come up with this number, black bodies don't have an infinite amount of radiation. Me and you don't create as much energy as the sun, or an infinite amount of energy. And he did the calculations and he came up with this number that kind of was just purely based on statistics and purely based on mathematics, and really based on the experimental phenomenon or experimental analysis. He kept on coming up with this number over and over again. And this number is what relates all these different factors. Like I said, the quantization of light, the quantization of atomic orbitals for Niels Bohr, which becomes very important, and also just the idea of atoms existing and ultraviolet, right, black body radiation not having infinite amounts of radiation. So that's a common theme in quantum mechanics is Planck's constant. At least it is for me. That's how I kind of shift my orientation. I'm talking about shifts. I want to talk about how quantum physics is a paradigm shift. It's a different way of looking at the world. And that's why it's so important to understand. And I think that's why physics students and physics in high school does a huge disservice to students by explaining the world through Newtonian mechanics, that things work in this like clockwork universe. We'll eventually find out things do not work out that way. But more importantly, the world doesn't work how Newton necessarily thought. He was a very important person in terms of generating equations and experimental analysis and getting us to where we needed to be. But again, you could argue the same thing of Aristotle. You could argue the same thing of Archimedes. These are all very important figures. Ultimately, Planck, Einstein, Niels Bohr, eventually Heisenberg, and so on, they become really the pillars of a new way of looking at the world. And that's really important because how we look at the world allows us to think about the world and come up with experiments to really test what we want to know about. If we have this framework of if I hit a billiard ball with one ball and the momentum pushes it forward, and that's how I think of the world is this a bunch of billiard balls on a pool table, that kind of creates a framework for me to think about the world in. And it does limit me to how I think about the world and what experiments I can do. So it's really important. It's as big as the shift, I think, as going from ancient Greece and the idea of just the indivisible substance being an atom to Rutherford's atom, which is the first real diagram we have of atoms, and then going to Niels Bohr atom, which is the quantum atom in terms of having these discrete orbitals around the nucleus. And that's what we're going to really talk about in the future. And once you start looking at the world through this framework, that there's a discrete graininess of the universe, that things aren't zero and things aren't infinite. And it's hard to understand because we see these terms in mathematics of infinity and zero. We see them, so we naturally think that the real world has these numbers and these sets. Ultimately, they don't. And that's what quantum mechanics is about, is energy gets really, really close to zero, but not quite. Not if you measure it really, really closely. The speed of light is really, really, really fast, almost infinite in speed, but it's not quite that fast. And c, or the speed of light, will be the speed limit of the universe. And the Planck constant is going to be the graininess of the universe. We can almost think of it almost as if we were looking at a movie theater film, it would be the frame rate. That graininess is what Planck's constant allows us to really look at and really think about the universe as. That's why these things are important. And we get into this in other philosophers. We'll talk about paradigm shifts. Kuhn, for example, and Wittgenstein will talk about paradigm shifts in science, and we can talk about science, the philosophy of science all day long. But if we really just start thinking about the world in terms of looking through the world now as a quantum world, in terms of there are quantities that I can have, that's a big part of it. The other big part will come later on in another podcast, where we start equivocating mass with energy. Newton didn't think of mass and energy as the same thing. They were related for Newton in terms of potential energy and in terms of velocity, but they weren't the same thing. To Einstein, energy and mass are going to be convertible. And that is going to allow us to leap to the idea that there are no such things as particles. Me, you, your dog, a ball, my computer, we aren't particulate. We seem particulate because we're very big compared to atoms. But if you actually take anything and we bring it down to absolute zero, we'll start seeing wave-like properties. Everything is a wave. And beyond that, everything is also almost like a field, because there are different areas of the energy of a wave that goes on almost infinitely. I'm going to bring that word back, almost infinitely. And so we'll start looking at the world in terms of fields, which is similar to a wave, but related, but and somewhat the same. But we're all waves. And the way to think of the world is really there are no such things as particles, which is a hard way to grasp that. But it is incredibly important, because it's going to allow us to start thinking of subatomic particles. It's going to allow us to unbox and understand how a particle can be different forms of itself. It can be different masses. It can be opposite in spin, or it can be different versions of itself. And eventually, we're even going to learn, if we accept string theory, that all particles are pretty much probably the same particle, or they're the same thing, just different vibrations in different dimensions. And we'll go over that. And that's kind of a very strange concept. And I think we can even start talking about how quantum theory is connected to string theory. Of course, they are connected, but beyond even what we know now, as we start getting into fractal geometry and start understanding more about geometry and applied string theory, we do see that there's certain dimensions that we can have. And we'll go into what fractals are. The most common fractal is a snowflake, the Koch snowflake, where it's a pattern that is infinite, has infinite digressions, and it creates different dimensions. So it goes from a one-dimensional figure to almost a 1.5-dimensional figure to a two-dimensional figure. And we'll talk about that in terms of you can have these in-between dimensions, but they're still discrete. There's not an infinite amount of them. And so if we start thinking, well, there's not an infinite amount of dimensions, there might be close to infinite amount, but it's not infinite. We have discrete units of fractals that dimensions can come in, that we can measure things in. Then string theory starts to make sense. Then it starts to make sense that particles are all related. They're just different vibrations in different dimensions. So this is all related and very important to understand. So I will continue to break down quantum mechanics, and we will hear more next time on cyclotrons and synchrotrons. Those are the two types of accelerators that we accelerate electrons or particles through to create more particles. And cyclotrons are actually used at the hospital. They're in PET scans. I started in radiation oncology, and we use them in the hospital. In gamma radiation, you have mini cyclotrons, basically, to produce high energy radiation. And I'm going to explain how cyclotrons and synchrotrons work and create these particles and energy. So until next time, follow me on Instagram and TikTok at Professor Matt W, and stay curious, my friends.